Let's take a look at geometric sequences. Today we're going to introduce this type of sequence. So pictures below show a square, and then suddenly we're splitting it into 5 squares. And then each square then gets split into 5 squares, and so on. And we get this really interesting pattern. It's actually, if it goes on forever, it's called a fractal. Because if you keep zooming in, it will look the same, in fact. But the point is that actually, if we count the number of squares, then we will actually create a geometric sequence because every time we are timesing by 5. So 1, 5, 25, 125, and believe it or not, 625. And that is essentially the definition of a geometric sequence. We're timesing, instead of adding a constant every time, like in a linear sequence, quadratic sequence is a little bit different. Where geometric sequence we are multiplying, and you can get some amazing sort of visual things with geometric sequences. You might want to investigate that a little bit more, or the idea of fractals. Now, my question to you is, what are some possible questions we could ask about this? So pause the video and think about it. It's always really good when you sort of see a topic, what can we actually do with it? Like, how can we link it to previous topics? What did we find then? Well, I've got a few answers. So we could ask maybe the number of squares in the next term, in the sixth term. We could even try and draw it. It's going to be a little bit tricky at this point. We could calculate the number of squares not just in the sixth term, the seventh term, the eighth term, but in the nth term, i.e., in any term. How could we do that? I'm not asking to work these out. I'm just sort of getting you to think about what we could potentially ask. We could ask if a certain number was in the sequence. Like the number 2 is not in the sequence because we jump from 1 to 5. There's no way we're going to then jump back to 2 at any point. And then, you might be interested in things like calculate the first term that's greater than 20,000. So just a few questions. You might have some other ones. I'd say the main one that I'm looking to get from you are probably these two. Okay, the next term is quite a common one that's asked, and the nth term as well. We're actually not going to answer these right now. We're just talking about some questions, but we're going to instead look at some other aspect and potentially come back to this. So, like I said, for a geometric sequence, we're timesing by something every time, and we say it's increasing by a constant multiplier or common ratio. So given that, can you identify which of these sequences are geometric? Which ones are timesing by a constant every time? Pause the video, try this out. So A, is it geometric or not? Well, it's timesing by 2, but then it's clearly not timesing by 2 again. It's not geometric. It's actually a linear sequence. It's going up by 4 every time. This next one, B, it seems to be timesing by 4 every time. It is a geometric sequence. C, again, it's timesing by 2, but then it's not timesing by 2. Immediately, we can say it's not geometric. This one here, actually, you can straight away see I'm adding 6 every time. This one is going to be a linear sequence. I'm not going to be timesing. I have to times by 7 here. Then it doesn't work there. It's not geometric. And finally, this one here, well, it's actually getting smaller. So you might say you're dividing by 2 every time, or equivalently, you are timesing by a half. It's okay to multiply your constant multiplier to be a fraction. It's actually also okay for it to be a negative or a negative fraction. It's actually okay for it to be a surd, which is something we're going to look at as well. So, for example, root 2, and then if I times by root 2, I'd get 2. This would be the start of a geometric sequence as well if I times by root 2 every time. Let's move on. So now I'm telling you that these are geometric sequences. How can we find the next term? Well, I'm kind of giving it away at the bottom, but the first one you can sort of see I'm going from 1 to -4. I must be timesing by -4, and then I can see that's happening again and again and again. So now I just need to do 200 256 times minus 4, and that's actually going to be minus 1024. That's going to be the next term in the sequence. This one's a little bit trickier to see because instead of going from 1 to minus 4, that's quite easy to spot. I'm going 20 to 12. So what I could have done here is I could have done the second term divided by the first term. That is actually going to tell me what I have to times by. So I can do the same here. I can do 12 divided by 20. And that's actually going to be 6 divided by, I can write that as a fraction, 12 divided by 20, which is 6 over 10 if I cancel it down. So it's going to be 0.6. So every time I'm timesing by 0.6, and I could check that if I wanted. So I'm going to have to do 2.592 times 0.6 to find the next term, which is, the fractions are getting smaller, it's going to be 1.5552. That's the next term. So be aware of that. Take this away. If we divide the current term by the previous term, so I happen to pick the second and the first, but pick any two terms and do the one after divided by the one before. So these two together, then you'll get the common ratio or your multiplier. And this is again a way of testing if the sequence is geometric, because you'd expect to get it for every pair of terms. So here's an exercise to test you on that. Can you find the next term of these geometric sequences? Pause the video, try this out. Some of them increasing, some of them decreasing, some of them switching between negatives. Here are the answers. So we're timesing by 3, timesing by 4, by 5, by 1.5 for D, I think. 3, I think it's by 2.5. Then we're dividing by 2 or timesing by a half. You can see here I'm timesing by minus 2. Here I'm dividing by minus 4, so I'm timesing by minus a quarter. Here I must be dividing by minus 3, so timesing by minus a third. Here I'm dividing by 5, so timesing by a fifth. Okay, you might not have left your answers as fractions, but hopefully you can check if they're okay. Right, here we go then. What about when we get some surds? Well, actually, I kind of already spoken about this one, coincidentally, but can you find the next term of these geometric sequences? Actually, I'm just going to say, give it a go, see if you can figure it out. For this first one, I'm timesing by root 2 every time. When I do root 2 times root 2, I get to 2. That's the definition of root 2. It's the number, when I times it by itself, I get to the number sort of inside the root. And again, I'm timesing by root 2 here, and so on. When I get to the next term then, it's going to be 4 root 2 times root 2. And the root 2 times root 2 is going to become 2, so it's going to be 4 times 2, it's going to be 8. This one here, a bit trickier to see. So there are two ways to do it. Probably the easiest way is to kind of do a sort of inspection. I can see that I'm going to need to times by root 3 to get rid of that root 3. And if I do that, it's going to become 4 times 3, that's 12. So I want to get to 24, so I'm going to have to also times by 2. So it's going to be 2 root 3. This probably could have been easier seen by comparing the second term to the third term. I can see if I times by 2, I get to 48. Then I also need to times by root 3. So inspection, probably the way to go here. A longer way to do it is to do what I said before. Take maybe the second term and divide by the first term. Only thing here is I'm dividing by a third, so I'd have to remember how to rationalize the denominator. I'm just going to go through that. So I could do 24 over 4, which is 6, so it's 6 over root 3. And then when you rationalize the denominator, for this one, you would times the top by root 3 and the bottom by root 3, which would make it 6 root 3 over 3. Because once you've rationalized the denominator, it's going to be much easier to simplify. You can see you get your 2 root 3. Now, to be fair, I'm probably not going a good choice here. It would have been better to do the third term divided by the second term, much easier in this case. 48 root 3 over 24, you can see that the 24 and the 48 cancel to give me 2 root 3. So I've explained it 3 different ways how I can get the 2 root 3. Just to finish it off then, to get this next term, it'd be 576 root 3 times 2 root 3. Well, 576 times 2 is going to be 1054 by doubling it. And then I'm going to need to times that by 3. Okay, and that is going to be 3,162, I believe. Let me just check. This looks good. So yeah, we've got a surd. We times by 2 root 3. We're going to get 3,162. All right. Given that, can you try these questions out? Involving surds, can you find the next 3 terms of the following geometric sequences? Leave your answers in surd form. Right, hopefully you pause the video, you've given this a go. I'll show you the answers. Here we are. So we're timesing by root 3 each time. For B, we're timesing by root 5. Here, by root 7. Here, 8 goes to 4 root 2. So we're sort of dividing by 2 and timesing by root 2. So we're timesing by root 2 over 2, or 1 over root 2 in fact. Here we're actually timesing by 1 over root 3. Okay, this one, they get a bit trickier in places. But hopefully you're happy about this. We've made a good start at geometric sequences. We've learned what a geometric sequence is. We have identified whether a sequence is geometric or not, and then we've been looking at finding the next term, including sort of dividing, or timesing by a fraction. We've had negatives, and then we've looked at surds. Coming up next, then, so we've done this first bit. Coming up next is this one here. How can we work out the term, the nth term, essentially? How could we work out the nth term of say this one here? Okay, that is coming up next lesson. Well done.